Welcome to Calculus Video 7, Developing the Power Rule. So the idea here is we have this limit definition of the derivative, but it takes a little bit, right? It's kind of takes a long time to work each problem, and we're going to get into some problems that are much more complex than the ones we've worked so far. It will make it really tough to continue to use the limit definition of the derivative. So what we want to do is try to make some shortcuts, some different rules that will make our life easier. So today is going to be really mathy. We're going to develop what's called the power rule, but you'll actually like using the power rule because using it will save you lots of time, even though today's development of it will be quite lengthy and a little complex, but I think you can handle it. Okay, so we're going to start with our function f of x is equal to x to the n. So n here is just some number. Eventually, we'll get n to be all the numbers in the rational numbers, right? So all the whole numbers, the negative numbers, fractions, things like that, except n not equal to 0. That's not going to work for this one, including eventually here n not equal to 0. We'll take care of that particular example with a different kind of a rule. But you're picturing things like this, right? You're picturing things like x squared, x cubed, x to the fourth, x to the fifth, x to the sixth. You know, what is the derivative function of those kind of powers, if you will, right? X to certain powers. So our goal today is to find f prime of x for f of x is equal to x to the n. We don't know what number n is. We're using that as a constant, an unknown constant. And we're going to use our very familiar f prime of x is equal to the limit as h goes to 0, f of x plus h minus f of x over h, our limit definition of the derivative to do this. Now, before we get into actually working this example, let's go back to some previous examples that we had. If you remember when we did f of x plus h, at one point we had an x squared. And we plugged in x plus h into the x squared, right? We had an x squared function, and we plugged in the x plus h, and so x plus h squared gave us x squared plus 2x h plus h squared. We multiplied x plus h times x plus h out to get that. And then when we had an x cubed, we had an example like that. I believe it was like negative x cubed or something. We plugged the x plus h into the x there, got x plus h cubed. We multiplied x plus h times x plus h times x plus h. I think we had a negative sign out front, but the point is we ended up with x cubed plus 3x squared h plus 3x h squared plus h cubed. We could continue this pattern, right? X plus h to the fourth, x plus h to the fifth. We have to do that in order to be able to plug something in to the f of x plus h. Understand the difficulty here is we don't know which n we are using. Is it n3? Is it n5? Is it n7? We have to get a generalized form here, x plus h to some power n, when we don't really know what n is. It's an unknown constant. That ends up being the difficulty in this particular section, but I think a really nice example. All right, kind of get us to expand our brains of thinking more abstractly here. All right, so what we're thinking of is we have this x to the n. We don't know what n is, and so we need to find x plus h to the n so that we can have the f of x plus h term. All right, so how do we do that? Well, we're not going to get just an exact answer because we don't know what n is. We need to get what's called a generalization. And to do that, we're going to kind of stop for a second and use what's called Pascal's triangle. But before I get there, do you see a little bit of a pattern going on here? So in our first x plus h squared, this one here, we see the very first term is x squared. In x plus h to the third, the first term is x to the third. What do you think the first term will be in x plus h to the n? I believe it will be x to the power of n. Whatever that n value is becomes the first term. X plus h squared, our first term was x squared. X plus h cubed, our first term was x cubed. X plus h to the n, our first term was x to the n. Okay, good. How about the second term? Notice I got a 2xh whenever I did x plus h squared. 2xh. But when I did x plus h to the third, I got a 3x squared h. Couple of things to note. The exponent 2 in x plus h squared became the coefficient 2. The exponent 3 became the coefficient 3. It's reasonable to assume that the second term, whatever that exponent n is, will be the coefficient of the term. And x will be raised to what power? Now, when it was x squared, x was raised to the first. When it was x plus h cubed, x was raised to the second. It's one less of a power each time. In this case, it's going to be raised to the power of not n, but n minus 1. And in all cases so far, it's been 2x and then just a single h. 3x squared and a single h. We can assume by pattern recognition that we'll have just a single h here. The third term's a little more tricky, but there is something of note here. The third term in x plus h squared had an xh squared. The third term in x plus h to the third had an xh squared. We don't know exactly what this might be, because it might be pretty complex, but we can kind of assume it's going to be something. We put a big box there, times h squared. Okay, and then plus, and this thing's going to go on until who knows how long. What do you think the very last term will be? Hopefully, you said h to the n. Just like the first term was x squared, the last term h squared, x cubed, x to the n, h to the n, with a bunch of terms we don't know in between. Now, I could just stop here and say, yeah, that should make sense. It's x to the n plus n times x to the n minus 1 times h, plus some other terms times h squared, plus some other terms. Notice that all the other terms here should have h to some power that's more than h squared. The next one should be h cubed, the next one should be h to the fourth, the next one should be h to the fifth. So the powers of h just keep increasing as it goes on. But I want to add to it a little bit to show you a little bit of math that might be useful for you later on as we try to kind of get a better handle on what x plus h to the n is. Let's talk about two things here. One is Pascal's triangle, and one is the binomial theorem. Pascal, Blaise Pascal, is one of my favorite mathematicians. In fact, I named my dog Blaise Pascal. This is Pascal's triangle. If you haven't seen it, it's good to take a look at this. It's useful in many ways, and what you'll see is it's a triangle with ones along the diagonal. Sorry, not along the diagonal, along the outsides. Go to outside the triangle. And so you'll see a 1 on the top, and then a 1 and a 1, then a 1, 2, 1. And where you get that 2 from is simply by adding the two terms above the 2. So 1 plus 1 gives us 2. 1's always along the outside. This next row, 1, 3, 3, 1, the 3 becomes a 3 because it's 1 plus 2 is 3. And this 3 is 3 because 2 plus 1 is 3. And this just keeps on going. 1's along the outside. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1's along the outside for this fifth row here. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. What would the next row be? Well, you'd have 1's on the outsides. 1 plus 5 is 6. 5 plus 10, 15. 10 plus 10, 20. 10 plus 5, 15. 5 plus 1, 6. And you see the pattern. If I just pick some rows out, 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, 1. It's a symmetric pattern. This is Pascal's triangle. And Pascal's triangle leads us into what's called the binomial theorem. And the binomial theorem is basically a way to find out what x plus h to some power is, right? Binomial, two terms, x plus h, and you could put a number in for h if you wanted to here. It really works either way, but we're dealing with x plus h's, so it's nice to keep it that way. So like I could do x plus 3 to the fifth, for example, but I just want to leave it x plus h for now. And to the fifth power, I'm just picking a number. What you want to do here is pick a row. And so this row here, 1, 2, 1, that is x plus h squared, gives that row. So the 1, 2, 1 are simply the coefficients that we're going to use. Go back up to the top, x plus h squared, right here. What are the coefficients? They are 1x squared plus 2xh plus 1h squared. Right? Pascal's triangle is giving us the coefficients for x plus h to some power. The row here, 1, 3, 3, 1, those are the coefficients for x plus h cubed. Right, go back up. X plus h cubed, the coefficients are 1x cubed plus 3x squared h plus 3xh squared plus 1h cubed, 1, 3, 3, 1. Then to find the rest of the terms, you simply decrease the power of the x's and increase the power of the h's. So for example, I have 1, 3, 3, 1. What I'm doing here is let's see, I'll try and see if I have room right here. I have 1x cubed with no h. Then I have x squared, so the power of x's are going down from 3 to 2, and then a single h. 3. X powers continue to go down. Now it's just x to the first, but h powers go up. It was 1, now it's 2. And finally 1, there was just one x, but now there's no x's. H went from h squared to h cubed. The powers just go up. 1x cubed plus 3x squared h plus 3xh squared plus 1h cubed. So for example, if I wanted to know x plus h to the fifth, I'm going to use this row right here. All right, this is x plus h squared, x plus h cubed. This one would be x plus h to the fourth, and this one x plus h to the fifth. So the coefficients for each term will be 1, 5, 10, 10, 5, 1. So x plus h to the fifth. I know the coefficients are 1. I'm going to have an x to the fifth with no h's. Then plus 5, my x's will drop by a power. Now it's x to the fourth. And I'll have a single h to the first power. Plus 10, x to the third. Again, the exponents for x are decreasing by 1. The exponents for h are increasing by 1, so now I have h squared. Plus 10, again, x's go down by 1 in exponent, so now it's x squared. H is increased by 1 in exponent, therefore x cubed. Plus 5, x to the first, h to the fourth, plus 1, no more x's, h to the fifth. And I've used the binomial theorem to expand x plus h to the fifth without having to do x plus h times x plus h times x plus h times x plus h times x plus h, which gets really long. This is a faster way to do that. Okay, now that we have that, let's take that idea and see if we can find out what is x plus h to the power of n. Well, we really don't know what n is. That's okay. Maybe? Maybe. We'll see. We're not going to get an exact answer, but we will get a generalization, or at least enough to get us what we need. It'll be 1, x to what power? X to the n. No h's. Plus, now what is the coefficient going to be? Once again, in the x plus h to the fifth, I had a coefficient of 5. Sorry, I had an exponent of 5. That became a coefficient 5 right there. That pattern is right there every time. You can see that the second term is 2, then it's 3, then it's 4, then it's 5, then it's 6, then x is going to be 7, then 8. That second term is whatever power was on the x plus h to that power. So we're going to have n, because that's the power, times x to the n minus 1 times h now to the first. Okay, what's the next one? Well, without getting into too much, let's just say we don't know. But here's what we do know. It's going to be some number, let's call it b, times x to the n minus 2 times h squared. And the next one is going to be some number, call it c, x to the n minus 3 times h to the third. And this is just going to keep on going all the way until we get to h to the n. Here's what I want to point out. Every term in the box here has at least an h squared. H squared, h cubed, h to the fourth, h to the fifth, all the way till you get to h to the n. We don't really know what the coefficients are at this point, but it's not going to matter. So what I'm going to do is I'm going to rewrite this as x to the n, 1x to the n becomes x to the n, plus n times x to the n minus 1 times h, plus I'm going to factor out an h squared out of all these terms that are left. I'm going to factor out an h squared. That will leave me with b x to the n minus 2 plus c x to the n minus 3 times h plus d, right, you just keep on going, plus h to the n minus 1, because I took an h out. And what I'm trying to say is the thing in parentheses here, this b times x to the n minus 2 plus c times x to the n minus 3h plus, I don't really know what it is. And so for ease of writing, I'm just going to call this some function of x's and h's. Right? Some function of x's and h's. That's all I really need. So this is equal to x to the n plus n times x to the n minus 1 times h plus h squared times some function, I'm just using this fancy O here, some function of x's and h's. Now, we kind of skipped all the way to Calc 3 for a second. We have multivariate functions, functions of two variables in this case. And we have not talked about that, but it's good to kind of get our mind around functions of two variables. And so what we're saying is this part here that I've kind of squiggled underneath, not the h squared part, because that has its own part, but this part that's in parentheses becomes this function of x and h that we don't really know what it is, but it doesn't really matter. It's just some function of x and h that is multiplied by h squared. Okay, this is, if you remember, this is x plus h to some power n. Now we can take the limit definition of the derivative. Our original function was x to the n. F of x plus h, we now know, is x to the n plus n times x to the n minus 1 times h plus h squared times some function of x and h. And so when we do the limit definition of the derivative, we see f prime of x is equal to the limit, as h goes to 0, of f of x plus h minus f of x over h. That's the limit, as h goes to 0, of f of x plus h, which is x to the n plus n times x to the n minus 1h plus h squared times some function of x and h minus f of x, which is x to the n, all over h. And while that might look like a lot of symbols, what we do notice is the x to the n and the negative x to the n cancel out, just like we're used to seeing in this limit definition of the derivative. This is equal to the limit as h goes to 0 of n times x to the n minus 1 times h plus h squared times some function of x and h over h. What you'll notice in the numerator, every term has at least an h. You have an n times x to the n minus 1 times h, plus h squared times some function of x and h. So we can factor an h out. The limit as h goes to 0. That doesn't look like limit. Let me try that again. The limit as h goes to 0, factor out the h. Then I'll have n times x to the n minus 1. I've taken out the h. Now I've taken out the h, so instead of h squared, I just have a single h now, times that same function of x's and h's, over h. Good. Once again, the h's cancel. This is the limit as h goes to 0 of n times x to the n minus 1 plus h times some function of x and h. And here's why I don't really care what happened, what exactly that function of x and h's was or is because I'm letting now h go to 0. And if this h right here is going to 0, 0 times that function of x's and h's is simply 0. So we get just n times x to the n minus 1. And that's it. And when we prove things like this, we often put a little box like that saying, yeah, we proved it. We're good. So what we know is for our original function, f of x is equal to x to the n, the derivative f prime of x is equal to n times x to the n minus 1. And that is called the power rule. We have developed the power rule that is going to make our life in calculus much easier, or at least easier for a while. And then what it really does is it opens up a lot more functions that we can take the derivative of, allows us to do more complicated things.